We're all talking about large language models, right? They're absolutely everywhere. But what if they're not the end game? What if they're actually a kind of beautiful, brilliant dead end? Today, we're going to dive into a pretty wild idea for what might come after LLMs. It's a whole new paradigm called fractal-like context-dependent dynamics, or for short, FCD.
So to really get a grip on where AI could be headed, we first have to get real about where it is right now. And this quote, wow, it just nails it. We're stuck with LLMs that only pretend to think. They're called frozen probability sculptures. I love that phrase. Think about it. Once they're trained, that's it. They're done. They become this beautifully carved, non-living memory structure. It's less like a living, growing brain and more like a perfect fossil. An amazing snapshot of a moment, sure, but it can't change, it can't evolve.
So here's our game plan. We'll start with the problem with today's LLMs. Then we'll get into FCD and this crazy idea of intelligence as a physical shape. We'll look at how it actually thinks, check out its roots in biology and physics, and then wrap up by asking the big question: is this the post-ALM future?
All right, Section 1. Let's dig into the big problem with large language models. Why is this idea of frozen intelligence just not going to cut it in the long run?
You know, this really gets to the heart of the critique. Tokens aren't thoughts. Embeddings aren't ideas. See, LLMs work by chopping up our world into these little pieces called tokens, and then they get really good at figuring out the statistical links between them. It's incredibly clever, don't get me wrong, but it's kind of like having a perfect map of a city. The map can show you the most probable way to get from point A to point B, but the map itself isn't thinking, it's not experiencing that journey.
And that leads us to this massive contradiction, right? I mean, think about your own thoughts. Cognition is a process. It's fluid, it's dynamic, it's always changing. So why on earth are we trying to build artificial intelligence on top of a frozen, static, statistical model? This question right here is basically the launch pad for the entire FCD idea.
Okay, so if these frozen models are the problem, what's the answer? Well, let's get into FCD. This isn't just an upgrade, it's a completely different way of looking at things. It suggests we think of intelligence as a shape. Yeah, a shape. This is more than just a new algorithm. It's a whole new ontology, a fundamental rethinking of what intelligence even is.
So here's the big idea in a nutshell. I want you to forget everything you know about digital code and weights and parameters. Instead, imagine a system that uses something totally analog and fluid, something like light. In this FCD world, intelligence isn't about finding a static final answer. It is the process of getting there. It's the dynamic, shape-shifting trajectory that energy or light takes. We're talking about a system that literally thinks through movement and transformation.
Let's break that down a bit. So instead of data being stored as ones and zeros, information gets encoded in these actual, physical, deformable patterns. They're called morphs. So what's computation? Well, it's just what happens when these shapes interact, when they bump into each other and relax into a new, stable form. And get this, learning isn't some massive offline training process. Learning is happening all the time. It's the continuous deformation of this whole landscape of shapes. Every single new input reshapes it, kind of like a sculptor constantly working a piece of clay.
Okay, this is probably what you're wondering. How does a system built on shapes actually think? It sounds cool, but what does it mean? Let's dive into the mechanics of this, the morphological paradigm.
So how does one of these morphs even come into being? Picture this. You have a calm, uniform optical field, like a blank canvas or a perfectly still pond. Now an input, let's say an entire sentence, doesn't come in one word at a time. It hits the system all at once, like a single wavefront, like dropping a stone in that pond. It creates all these ripples, right? Interference patterns everywhere. Most of them just fade out. But some patterns, through resonance where the waves reinforce each other, they stabilize, they persist. Those persistent patterns are the morphs. They become living memories, physical encodings that are constantly being reshaped by the next input.
And here's where you can really see the night and day difference. An LLM is all about next word prediction. It's like it's assembling a sentence one Lego block at a time, always guessing the next most probable piece. FCD, on the other hand, is what's called analog semantic relaxation. The entire input creates a single meaning shape that then just settles into a coherent state. It's not step by step, it's holistic. It's the whole thing all at once finding its equilibrium.
Let's use a classic example. The quick brown fox jumps over the lazy dog. An LLM processes that one token at a time, the, quick, brown, and so on. But in FCD, that entire phrase hits the system as a single wavefront. Instantly, it activates a bunch of existing morphs. Patterns for things like animal motion, speed, maybe color, past tense, and all these different shapes interfere and merge and resonate together until they relax into one single, coherent meaning shape. That final, stable shape is the understanding. It's not a sequence of words, it's a unified concept.
Okay, now we're going to zoom out a little because this is where the idea gets really, really deep. FCD isn't just being pitched as a clever new computer design. No, the argument is that it's tapping into the fundamental rules of biology and physics. It's what's called a thermodynamic narrative. This right here is such a powerful analogy, computational morphogenesis. So, morphogenesis in biology is how life creates incredibly complex shapes, like an embryo, from a pretty simple set of rules. The idea is that FCD does the exact same thing, but for thought. The morphs are like the cells. The energy gradients in the system are like the chemical signals that tell the cells where to go. So the system isn't calculating an answer in the traditional sense, it's growing an answer, organically.
And this quote, this one really connects FCD to one of the most fundamental laws of physics, entropy. You know, the idea that the universe is always moving towards more disorder, more chaos. But life is this weird, beautiful exception. It creates these little pockets of incredible order. That order is what we call negentropy. And the really mind-bending insight is that by creating this local order, life actually helps the universe increase its global disorder even faster. It's a strange cosmic bargain.
So the whole point of FCD is to copy that exact process. It's designed to be a machine that creates local order, those coherent meaning shapes we were talking about, out of a chaotic input. When you look at it this way, FCD isn't just a computer running code. It's taking part in the very same fundamental dance between order and disorder that creates a snowflake, that drives a hurricane, that builds a living cell. Suddenly, intelligence isn't just abstract math anymore. It becomes a physical phenomenon.
Okay, so this all sounds absolutely incredible, right? Maybe even a little bit like science fiction. But what does it really mean for the future of AI? Can we even build this? That brings us to our final section, the big debate about the post-LLM future. This chart really lays out the whole argument in one go. You look at LLMs, they have static weights. They can't learn after training. FCD is all about continuous learning from every single input. LLMs are based on token causality, which is really just statistics. FCD is about morphological context, where meaning is dynamic and holistic. LLMs can be brittle. FCD is adaptive. And maybe the biggest difference of all, LLMs are abstract computation with no real link to the physical world. FCD is explicitly aligned with physics, with entropy and morphology.
But the billion-dollar question is, can we actually build it? And the debate really comes down to these two sides. You've got the visionary who says, hey, look, biology has already solved this. We have proof of concept. It feels too beautiful not to be real. But then you have the pragmatist, the engineer, who's like, whoa, hold on. The physics sounds promising, but trying to control a chaotic dynamic system of light and energy, that is an absolute engineering nightmare. How do you keep it stable? And how could you possibly control it or even know what it's thinking?
So where does all this leave us? Well, the synthesis seems to be this. FCD is feasible enough that we should be trying to prototype it right now. It's also potentially dangerous enough that it really matters that we understand it. And maybe most excitingly, it's alien enough that whatever we end up building is probably going to surprise us in ways we can't even imagine.
And that leaves us with this final, really provocative idea to chew on. The future of AI might not be digital, or symbolic, or even probabilistic. It might be analog shape evolution in a morphogenetic substrate. What that really means is the future of AI isn't about writing better code, it's about building systems that think by physically becoming the answer. It's a complete shift in how we define computation, and it forces us to ask a really big question. Is the next great leap in AI going to be a breakthrough in software or a breakthrough in physics?